So I was actually a PhD student here back in the dark ages and went into aerospace engineering because even in the 1990s it was pretty, shall I say, intuitively obvious, I know that's a terrible phrase, that AI would play an important role in decision making for aircraft and spacecraft as well as other domains. So I found my place as an applied AI person. For some people, applied is good, for some it's bad, but that's where I am, specifically with respect to things that fly. So one of the places that really hasn't been studied all that thoroughly in the research community is how to apply AI to improve safety, not capability as much as safety. All right, so now I'll stand next to this and click and hope things work well. Good. If you look at aviation writ large, right now we have tons of commercial transport operations, the big jets that you fly when you go to Detroit and other airports. We have general aviation, the Cessnas et al., that you find at the smaller airports. Those know how to share the sky. There's been long-term voice-based air traffic control and rules that they follow to make sure there's lots of spacing en route, miles in trail. On approach, you follow a particular aircraft. You know that the patterns are such that you won't cross. Now you include the new entrants, the Unmanned Aircraft System, UAS, and the Urban Air Mobility Platform, UAM. UAS are not expected to follow point-to-point routes to a great extent. They'll be flying low, surveying structures like bridges, inspecting crops, delivering payloads to whoever needs them. They're not going to fit into the rules, and they're not going to be able to communicate by voice. So what that requires is that we rethink aviation. As a starting point, we're looking at very low altitude airspace, you know, that airspace that we never thought airplanes would fly in back when airplanes were big and human piloted. And now we realize, if you put on a safety hat, that even though we're starting there, and it may make sense to deliver a Jimmy John's sandwich or a taco with a tiny drone, it's not going to make sense to deliver 500 pounds of payload, like you and your two closest friends, from point A to point B under 400 feet, because now you'll be flying through the urban canyons of Manhattan, because those buildings go above 400 feet, above ground. And if you fly 400 feet above those buildings, you're already in the airspace that is overpopulated with commercial traffic today. So that means that what we really need is advanced aerial mobility, where we mix all of these different traffic types together. And now we breathe deeply and we say, how do we do that? Well, it's a hard problem, and a lot of people are trying to make some progress. But here's kind of the categories of decision and perception and action functions, thinking robotics like, that we might have to perform. And these apply to any vehicle ranging from your backyard quadcopter up to the most advanced aerial mobility platform you could imagine that will not have a pilot either on board or in a ground station in the distant future. That's just the way it is. Now, not everyone would agree with me, but that's my position. And it will be for safety purposes. Now, let me pause and say why. If you have ever been in an Uber, Lyft, or other shared ride vehicle, then you kind of cross your fingers before you get on board, hoping that you have a good driver. Now imagine that someone with similar experience in driving is asked to fly across town. Right? They're not going to have that deep set of experiences that a commercial transport aircraft pilot has. So even though today, when you get in the back of a jet and go to sleep or watch a movie, you expect two well-trained, very conscientious pilots up front, you're going to get the Uber taxi driver, and I have no problem getting in Uber myself. I've done it a lot. Usually I feel very safe. But those people are not going to be ready to save the day when something goes wrong, which means that autonomy needs to do it instead. We just don't have the pilot training pipeline to do anything else. So these are the functions that we need, and by now you've probably read all 6 of them. So I'm going to go on to what I'm obsessively focused on, and I would claim that it was my AI background that led me not to this pathway to autonomy through piloted aircraft becoming simpler and then automated, or the UAS going all the way to the autonomy stage. I'm going to fast forward because there's not much time, but instead thinking about abstractions and knowledge representation. Right? One of the things over the past 20 years of being in the aerospace community that is absolutely clear to me is that there's a status quo of representation of information, and that is the underlying physics-based model. There's nothing wrong with that model. It's very powerful, and it can be used to optimize trajectories, to ensure stability of a control system, to model the aerodynamics, the propulsion system, the structure, but it doesn't really capture in a sufficient way how people have interacted with these vehicles over the past 100+ years. The first thing as a pilot that you think about if something goes wrong is aviating the airplane. Okay, fine. The physics-based model can usually do that well, as long as you have the proper adaptive control and system ID and all of that. The second thing is navigating. So navigating, if you have GPS and you have a good state estimator, is also physics-based and pretty intuitive. If GPS fails, you have some traffic near you, but they're clear, and you have to worry about buildings and all of that stuff. Navigation becomes a little harder, but we have a set of tools in the robotics community that can begin to address that problem. Communicating means telling everybody what your intentions is, whether that person is a human or another autonomous craft. Well, when something goes wrong, you do those things, but then you have to make decisions. The most important thing in an emergency is to do the equivalent of pulling off to the side of the road. The only problem is there is no roadside right there. So you have to select a landing site and you have to go there. The community that thinks of physics-based models for many years has been very adept at defining a cost function based on distance, time, and energy, and optimizing over those metrics because they fit very nicely into the physics paradigm. They have not done as well with creating new metrics, using new data sources, and understanding how that cost function can affect the decisions not only for the path to a prescribed landing site, but also to a landing site that you might not have anticipated would be required when you first started flying. So that's the goal of what a lot of our research has been, is to use new data sources, new metrics, new models for contingency flight planning. So this describes research that we did when I first became a faculty member, and I realized that no one was looking at landing sites, right, which are objects. You don't want to think of them as GPS coordinates. You think of them in terms of their feasibility for the aircraft. So when an aircraft has trouble, you first look at the place that it can go, the footprint on the ground. And then you find landing sites in that footprint that are feasible. Our early work looked at runways because that's the ideal place for someone to land in an emergency. And then we used constraints to eliminate those that were too short, had too much wind, et cetera, and then prioritize them. And then you could use the trajectory optimization strategies that have been developed for a long time. That was in 2001 to 2004. This Hudson River accident happened in 2009. It's a very nice case study because right now you can get all of the black box data downloaded from the NTSB accident docket website, plot it, and then think about what might have been done from an autonomous perspective to make it better. So in this case, we downloaded the data and then realized that we actually already had the tool to plan an emergency route back to LaGuardia. So in this case, we applied exactly the flow chart on the last diagram. This is just showing the takeoff. The little black square at the top really shows where the plane had to make a decision before it started descending into the Hudson River. We used a very simple, real-time, guaranteed to work, non-machine learning, I guess non-AI, path planner, and ranked the 3 LaGuardia runways. The top ranked one is the one where you'd have a headwind. You have no thrust reversers if you've lost engines, so having a headwind is desirable. If you waited 4 seconds after that black square, you could no longer go around and get back to that runway. So now you had to either land upwind, which means the wind is behind you, or crosswind. If you wait an additional 8 seconds, you can't get to anything. And then you have to land off of a runway. There are 2 lessons learned here. First, voice-based air traffic control is slow and error-prone. Maybe that doesn't surprise you, but this case study makes it extremely clear that that's the case. Sully did the right thing. He was calm. He conveyed efficiently the information to the air traffic controller, but he wasn't panicked. That was a problem. He should have screamed at the top of his lungs, even if he was calm, that we're all going to die. We need an emergency, right? Because then the air traffic controller would have routed everyone else out of his way. As is, it took them more than 16 seconds to recognize that he had lost both engines because his voice was calm and he was just reporting the facts. And then there was no way back. Right? So, choice number one, make data link happen. Right? Choice number two is always sound panic if you want priority. So anyway, there's that. The second thing is that even a very simple, not fancy automation aid that just chooses a landing site based on runways and simple trajectories would have been a really important automation aid to have, and it still doesn't exist today, even though it could. That's another discussion. I don't have much time. So where we went from that is to obsessively say, what about all these new entrants, these unmanned aircraft that are going to be flitting around below 400 feet over urban areas? We have to do something with them. And so then we looked at the literature, we did some research ourselves in real-time sensor data processing, which of course uses all of the glorious machine learning techniques to pull in LiDAR vision, approximate where the vehicle is with landmarks around it, perhaps do inertial navigation as well. And the first thing you recognize is that it will be very hard to certify that kind of system because you're using everything that the FAA fears. Now, it's worthwhile, because if you truly are in an unknown environment, that's the right thing to do. This flowchart shows the right thing to do, in my opinion. When you have a failure and you have to land soon, you look at the local area and ask, is it safe? If the answer is yes, you land. That's the whole sensor-based path planner. If you are not able to find a safe area within range of your sensors, you're best informed by understanding what else is out there. Your onboard sensors can't help you anymore, and it's not necessary that you need other vehicles giving you this information in real time, because we have a lot of data that's been stored in various forms on a cloud that let us do that. So our research is then focused on map-based planning to guide the vehicle toward a safe landing site that would be beyond local sensor range. For this purpose, we looked at open data sources, geographical information system, which has a lot of LiDAR and video data, OpenStreetMaps, which gives us roads, overpasses, land use types, building footprints, lots of stuff, as well as census data and cell data fused together to give us two different maps. One is a set of landing sites along with their risk, and the second is a cost map of the whole region, which can be represented as a heat map. This is an example of finding landing sites on roads in Manhattan. So if you look at the road network, find straight, unobstructed roads, and then you ask the question, which direction is traffic flowing? Then you get asymmetric segments that you could use for a fixed-wing aircraft to come down and land. This is actually something that pilots have done a lot, right? If you have an engine failure and you have to land, a straight road is a good choice. But now you have the ability of bringing in new data sources like traffic to look at speeds and densities, and you can treat the road like an entrance ramp. That's something that you could do with data that you couldn't do with a human pilot. Until they were right there, and then they can't try again. This is showing a heat map of occupancy. In Milan, Italy, where there was an open call detail report data set over a couple of months, we statistically processed it. What we found is not only are the routes changing because the occupancy changes so much, that's expected, but also the cell phone data is good during the day, the census data is better at night when people aren't using their phones, and special events can be deceiving. In this one data set, there was a World Cup soccer event that you could watch people go in, you could watch people leave. It looked like no one was there during the game, right? So that actually is an interesting problem if you have enough of this data of processing different data sources together to understand the true occupancy over time. This is a case where we used a two-stage neural network random forest classifier system to obsessively classify rooftop shapes. The reason we were doing this is not for architecture, it's to find emergency landing zones for unmanned aircraft, which are small enough that they're not going to break through a structure. All you need is a flat open spot. If you look at areas like Manhattan, you aren't going to really be safe landing on any street or park, surface, et cetera, because there's not open space where you don't expect people. So the rooftops are a good alternative. So we did this looking at 3 cities. Witten, Germany, where someone had gloriously already classified roof shapes. I don't know why. Manhattan, where a student gloriously spent 2 months of their life classifying roof shapes. I know why, but that probably wasn't very pleasant. And then Ann Arbor, where we classified manually roof shapes downtown. So then we looked at Witten, Germany, manually removed bad data, which also was painful for the student, and determined that we could get about 97% accuracy if we combined RGB and LiDAR results. So when we went to New York, we had more problems. Obviously, all of the infrastructure that surrounds buildings has to be put on the roof because there's no available land to put it on. So we ended up with an unknown class for malformed images and a complex flat class to deal with places like New York with complex rooftop data. At this point, we tested Ann Arbor without training on it using a network that had been trained on both Manhattan and Witten, Germany, and the results weren't quite as good. We're at 86, 87%. Now that wouldn't really be astonishing if you were using a fully autonomous pipeline, because then you would land potentially places that didn't actually have a clear landing site. But we did two things. One, we took the point cloud data on the roofs that were classified as either flat or complex flat, and then we took the data, processed it in more detail to find a maximally sufficiently flat inscribed circle, so that we were able to cut out obstacles and holes and create an area that then we could compare for size to select the largest nearby landing place. At this point, we now have two metrics which compete with each other. You always want to land at the place with the lowest landing site risk. You also want to follow a path that has the lowest risk. You can't have both at the same time. So the best you can do is build a list of potential landing sites and know their risk, build a list of potential paths to those landing sites, know that risk, build a Pareto front, and then make a trade-off. So circling back in my -1 minute that I have left to the Hudson River case. In that case, the landing site risk would have been extraordinarily low for LaGuardia, presuming they could get back there, but it was extraordinarily high for the Hudson River. So if you look at having a low landing site risk, you would have had something probably under 0.2, which is normalized if you landed on an aircraft, on a runway that was designed for that airplane, probably near 1 in the river. Path risk would have been very high for going to LaGuardia, because you were flying over a densely populated area with an airplane that had been damaged by birds and had no thrust to get back there, right? Whereas it was quite low to fly into the Hudson River because there was water. Those would form 2 points at extrema on the Pareto front, and there really wasn't anything in the middle. So that's kind of the case where we need to have these conversations and discuss as a community what we want to do with these unmanned aircraft, and then allow our tools, our machine learning, our data collection and mining to guide these vehicles as we move forward. But if we ignore the possibility that these vehicles can and will need to have emergency landings, we're not going to have as safe a system as if we address all of these problems now. Thank you.
Time for a few questions.
I've scared you all with the airplanes that are crashing in the Hudson River. Anything? Oh, yes.
I have a very general question. I'm curious to know how much AI is actually implemented in the cockpits of the commercial jets, like the Airbus or Boeing families.
Zero. No, I mean, so I think people have thought about how to display data to crews. And so they have tried to use kind of behind the scenes models of data processing and presentation that might have been guided a little bit by some of the principles found in AI. But right now, certainly you wouldn't have machine learning because you can't safety certify it, right? So what the community is talking about right now is using learning, but having a wrapper around it that imposes limits on what it can do. And that's, definitions of AI are multiple. I don't think we have any software in the cockpit of commercial aircraft that is human-like in its decision-making. It's usually very regimented guidance, navigation, control type functions, fuel calculations, optimizations of routes that support the crew.
May I continue my question with how much potential do you see for AI to be really implemented, knowing the advantages and disadvantages and the randomness involved in the AI?
Yeah, so if you go back to my first slide where I had commercial transport, general aviation, UAS, and UAM, I'm going to answer that question 4 times. For commercial transport, the promise is extremely low because people are comfortable with 2 pilots up front. There's a great legacy of equipage as well as practices that's going to keep the status quo there for a while. General aviation wants to go punch a hole in the sky and have a good time. So the people who already own their airplanes, the best that you can hope for them is to upgrade to equipment that will assist with detect and avoid when we have the small drones that they can't see in the sky. With the UAS and the UAM, they really hunger for this type of technology because UAS right now can only be flown line of sight in most cases, and the waivers that I have seen are not granted based on capability and that sort. They're based on, oh, you're far enough away from people that you're not going to hurt anyone, right? So we really have a disconnect between what we're able to certify and what we need for that type of operation, because the reality is someone sitting in a control station that can't see the vehicle doesn't have any more information than the onboard software does. They can't. So whatever decisions will be made are limited to the same data the software has access to. Therefore, there's great promise. With the urban air mobility, think Uber taxi driver and think how nice it would be if we had an extra passenger in these vehicles.
Time for one more question up there.
We have used the same analogy in medical imaging where it's very critical that FDA has very strict regulations. And what they are using is, instead of like AI taking over or reading the report, AI prioritizes. So can you apply the same principles in aviation, that it kind of gives the pilot like 2 pathways and then it's up to the pilot wherever they decide?
So I'll be happy to share the master's thesis from my University of Maryland student in 2002 that did exactly that for the runways that I showed for the Hudson River case study. The problem with that is when you're flying under 400 feet with a UAS that really is in trouble, you only have potentially 1 or 2 seconds to do everything that you need to do, right? So that's not going to be something that flies for minutes to a rooftop that's over the next block. That's going to be for the case where you use your sensors and you come down. But if you have a remote operator and you're flying low, I'll tell you from personal experience, that plane crashes before you ever notice that it's crashing. So for that, you need that millisecond response time that you're going to have in software that's impossible to interact with a human for. Now, suppose you have longer amounts of time. I think this is indeed where we're going. There's something called Simplified Vehicle Operations, or SVO, that is very seriously being considered for the UAM industry. And in that model, what we're looking at is having pilots trained to use that type of interface, where they get pre-processed data. They don't have to have a lot of stick and rudder skill. They have diagnostic skill and decision-making skill. So I think that's a great suggestion, and I hope we get there soon.
Great, thank you so much, Ella.